I have to unmute myself too. Caught onto that. Probably took me forever. All right. Do we want to wait a couple minutes to let the next few people get started? We usually wait 5 minutes before.
As you like.
But here, you know, it's not like we have to let them find seats.
That's true. I leave that choice to you. I mean,
yeah,
I can skip slides down the line if I have to.
Well, yeah, you've got you said you have this whole long talk, so there's that. Okay. Somebody told me they couldn't hear me anymore. Makes perfect sense. Yep, that is fine. I muted myself, so I deserve it. Okay.
Should I open up the chat window too, just in case people have questions?
Okay. I think that at the beginning here, I'll spotlight myself, and then I'll this one. Let's see here. Oh, I got muted again. Are people still hearing me or no?
I'm hearing you just fine.
I accidentally muted you and unmuted you. It's because we both admitted someone at the same time.
Ah, okay. It's all spite. I get it. It's fine. Okay. Okay. All right. Well, folks, welcome. This is now officially the largest Zoom meeting I've ever hosted. So thank you all for being here. This is the first edition of our 2020-2021 James Kaler Science Lecture Series. And at these talks, we always invite some speakers who work in the sciences to come share their research or a topic of interest of themselves. We've had a wide variety of speakers as we've been doing these talks for over 30 years. And it is my pleasure to introduce them, introduce our speaker tonight. And we've got a few speakers lined up over the course of the next several months, and based on how things are looking, it looks like those meetings will also be on Zoom. But nevertheless, thank you all for joining us. Before I introduce this speaker, I wanted to remind the people who are on here and looking to earn extra credit for attending one of these talks. My recommended way for us to track who you are is to please go ahead and rename yourselves. Okay, that means that you put your name, put the name of the course that you're taking, and then put the last name of the instructor. We've got some great examples listed in there in the participants, where we've got some people who are taking Josh Weber's Physics 141 class, for example. So they'd want to write PHY 141 Weber on that. So please do that, and it will really help us out with distributing this information back to your instructors. It's much appreciated. Now, I'm going to go ahead and I'll keep talking, but I'll switch over to gallery view so that you can see our speaker get embarrassed as I talk about him. All right. The other person sharing video at this moment is Waylena McCulley. She is the producer at the Staerkel Planetarium. If you look around at the background of her camera, you see she's actually in the dome. Yeah, the dome has not been completely mothballed. Isn't that nice? So the dome is actually being used from time to time for some very private events, usually using just the college. But Waylena is going to be sharing that software for Fall Prairie Skies tonight. So after Dr. Narayan's talk, feel free to stick around and you will get a showing of Fall Prairie Skies, and she'll be running that show a little bit after 8. Okay, so you don't have to change Zoom meetings. You can just stick around with us, and I hope you enjoy that. Okay, so our speaker is I believe, are you an assistant or associate professor over at the?
I just started last year.
Okay, all right. Well, you're on the tenure track. You'll be doing fine, I'm sure. Okay, so his name is Gautham Narayan, and he can critique my pronunciation on that one however he likes. I'm very sorry about that. He earned his bachelor's degree at Illinois Wesleyan, you know, just up the road. And then eventually he moved on to Cambridge, is how they usually say it, or Harvard University, I guess. And then last year he joined the University of Illinois as a professor in the Department of Astronomy. But while he was working on his postdoc, he happened to work also at the National Optical Astronomy Observatory, and he also worked at the Space Telescope Science Institute. He is going to be sharing with us all sorts of information about astronomy, about the history of observations, about how we manage the sheer amount of data that we receive from those observations. And as I said before, I will start to spotlight him. We'll keep his video pinned up there as well. Actually recording this. Well, Wheeleen and I will keep an eye on the group chat. So we might take the time to go and interrupt. If you want to throw questions up in the chat, that will be fantastic. You see that Dr. Narayan is now sharing his screen. So please feel free to offer any questions that you have. Maybe he'll be able to notice them, but we will be here to monitor the participants' chat and see how well we can address that. Okay, take her away, sir. Thank you so much for joining us.
So first of all, thank you so much, Eric, for giving me the opportunity to do this. I know from teaching class this semester that doing things on Zoom is just a little bit different. There's something missing that's there in this in-person interaction that we can't quite capture. But nevertheless, this is a really important thing for me to be able to do, because there are only something like 10,000 professional astronomers in the world, period. And yet the reason we can get billions of dollars of funding for things like the Hubble Space Telescope, from which the background in this image came from, is really because of the public support that we get from folks who are here on calls like this, listening about astronomy on their free time on a Friday night. And it's such a privilege to be able to do this. And so thank you very much to the folks at Parkland for giving me this opportunity. So the stuff that I'm telling you about today is really looking at the sky / with artificially intelligent eyes. And I'll tell you why we're doing that in a bit. So the sort of first question you might ask is, why do we have telescopes? Why do we have sky surveys? Why is there a need for AI? What's the big picture? And part of this is that astronomy is really one of the oldest sciences that we have, and it's cultural studies in a very, very real sense. Ancient cultures across the world have been looking at the night sky for forever. So take, for example, a place that's pretty close to Tucson in Arizona, where I did my postdoc, the Chaco Canyon in New Mexico, is a home for the Anasazi people. And well, what you find if you explore Chaco Canyon are a bunch of petroglyphs on sites, things like this. So here's a petroglyph depicting a crescent moon, a hand for scale, and a bright star near it, and there's something sort of fuzzy on the ground. And if you do a diagram of this thing, there's all sorts of interesting structure that you can see, and there's all sorts of interesting connections that you can make. So given we know when the Anasazi inhabited this canyon, what we think is going on is that they've made a pictograph of an exploding star in the sky, Supernova 1054. Now we know from the historical record that the supernova blew up on the 4th of July, back in 1054. And if you take your app to look at the sky and you rewind time all the way back to 1054 to the 5th of July, you'll find a crescent moon in the first quarter, much like is in the pictograph, and about 3 degrees away from that crescent moon is supernova 1054. The Anasazi seem to have lived in this area of New Mexico at a very, very interesting time astronomically. It's not just that stars happen to be blowing up. In 1066, there's another visitor in the sky that hadn't been seen before for a while, Halley's Comet. And perhaps that's what they're drawing at the bottom. So what you're seeing is that astronomy is a very visual science, but what the Anasazi are actually doing here is classification. They've already sort of labeled something as a star, something's a moon, something's a comet. They're trying to distinguish different astrophysical features. There's a scale, hand scale here for to give you a sense of how large things are. And they're already effectively beginning to do the science of astrophysics. But of course, naked eye observations are really limited. And it takes a Dutch invention, the telescope, to really start getting things to be better. Now, the old telescopes that Galileo and company had were really only a few centimeters in diameter. But they were really exceptional things because they let him see stuff that you could not possibly see with the naked eye. If you look at something like Venus or Jupiter with your naked eye, it looks like a bright star on the sky. And if you look at it for a long period of time, you can tell that that star is not really moving the same way as everything else in the sky. And so they were called planets from Planatia, wanderers, because they moved across the sky in a different way. So these telescopes now are really giving us higher magnification and better resolution to get a better picture of the cosmos. And what Galileo was able to see for the first time must have been tremendous. Now, if you go look at the moon out in the night sky tonight, when you peer through some of the clouds, you'll see some light and dark spots. But him looking through the telescope for the first time at this structure was able to draw beautiful diagrams of craters on the moon, how they change with phases, how the shadows change. And so here's an actual diagram from his notebook. And you can compare that to an actual contemporary picture of the moon today. And you can see that he's clearly marked out where the Copernicus crater is on the moon. This is really tremendous revolutionary stuff that's happening in sort of the middle of the 16th century. And now that you have a telescope, you can start doing survey astronomy. You can start looking at the sky systematically and looking for objects. And arguably the first person to do this for time domain studies, for things that change with time, was a gentleman of France named Charles Messier. Now, Messier was looking for comets, and he was very frustrated by the fact that things he was looking for, these comets that he was looking for, were fuzzy, but there were lots of other fuzzy things in the sky that didn't move like comets and were just stuck in one place. And so he started making a list of these things, a list of 110 objects that were fuzzy, faint, looked like comets, but didn't move in the sky, so that other people could ignore them and go hunt for his comets. Now, little did he know that he was making one of the biggest lists of interesting deep sky objects that there were. But what Messier has really done is taken a bigger telescope and started making a systematic catalog of the sky to learn more that we will see. And you can see Messier's 110 objects here on the right-hand side. And these images now are taken with things like the Hubble Space Telescope or small amateur astronomy telescopes. They include things like clusters and galaxies and nebulae. And we'll see lots of things. But to the telescopes of the time, which were still relatively basic, they all just look like fuzzy little blobs. If you look at one of those fuzzy little blobs today, M1, Messier 1, that's the remnant of the supernova that the Anasazi had sketched in Chaco Canyon. And because Hubble can look at this supernova over time, you can actually look at the time counter on the top right and see that 1,000 years after the star exploded, the debris from that explosion is still expanding outwards. And in the center of what remains there, there's a spinning neutron star that's emitting radiation that you can sort of see as ripples. So really, really beautiful data that you can look at with modern telescopes. And now that you're doing time domain astronomy, you can start to look at the stars themselves that seem to mostly be stationary. But not all of them are. Some of them actually start to pulse over time. So this is a star called Ares Puppis, and it's a star that's called a Cepheid variable star. It has a very periodic change in its brightness. So it gets brighter and dimmer over time, and you can actually see the brightness and dimness reflected in this fact that there are ripples in the gas surrounding Ares Puppis, which reflect the light from the star as it gets brighter and darker. These are light echoes, if you like. And so you can see this star pulsating. And it turns out that this sort of star that Ares Puppis is a very, very important variable star, a very, very important thing in the time domain for us to study. Because it's got this periodic behavior, and you can see this relationship between its period and its brightness, you can start to look at a whole bunch of these stars in galaxies that are near the Milky Way. In fact, if you go up to the southern hemisphere, say in Chile, and look up at the night sky, you will see satellite galaxies to our own, the Large Magellanic and the Small Magellanic Clouds. And systematic surveys with telescopes, much like Messier and other people were doing, were used to record observations of these satellite galaxies to our own and find these stars that varied. And some of them have short periods, some of them have slightly longer periods. And one of the women who was a pioneer in astronomy at Harvard, one of Harvard's computers back in the day, found that there was a relationship between the period of the Cepheids and how bright they were in an absolute sense, or how far away they are. So effectively, if you could measure the period of these stars by just taking repeated observations, you could get a distance to the galaxy in which these stars are. Of course, we don't know the galaxy yet. We're still calling them fuzzy nebulae, like Messi. And this relationship is called the Leavitt Law, and it's named for Henrietta Swan Leavitt, who first discovered this. It's one of the most central and important relationships to understand our universe to this day. Scroll forward a little bit to Edwin Hubble at Mount Wilson, which has remarkably survived the Bobcat fire in California. Yay, yay, yay. Hubble starts surveying these fuzzy nebulae for which we have redshifts. We understand how fast these objects are moving away from us, but we don't know how far away they are. We don't know their distances. And what Hubble is doing when he's looking at these nebulae, including objects that Messier cataloged, is that he finds some Cepheids. And because he knows about the Leavitt Law, he's able to calculate the distances to these fuzzy nebulae. And he realizes they can't possibly be within our galaxy. They are so far away that they must be completely separate island universes almost. One of the first stars that Hubble saw was in a galaxy called M31, which we know and love today, called Andromeda. If you go out on a clear night, which is not like tonight, and look up sort of at the constellation Cassiopeia, which is a W, and follow the arc of the W down, you'll find a faint fuzzy blob that if you were even a little bit out of the core of town, you should be able to see with your naked eye. And that's the galaxy that Hubble is looking at. And he sees one of these Cepheids for the first time on an image that he takes with a glass plate. And he is so excited when he realizes that it's a star that he puts an exclamation point with a var next to it on the glass plate to find it. We can actually locate the star that Hubble saw with the Hubble Space Telescope. That's named for him to this day. And this gives us a distance to Andromeda to match its velocity that we already have. And so Hubble does this for a whole bunch of these fuzzy nebulae and finds what's called the Hubble Law. Well, he actually called it figure 1, but nevertheless, it's a plot between the velocity of things and how far away they are. And Hubble plotting it, velocity versus distance, finds that the two are proportional to each other. The farther away something is, the faster it's moving away from us. The universe is expanding. There are galaxies that are outside our own. And remarkably, we've only learned this 100 years ago. Right? Hubble wrote this paper in roughly 1922 or something of that nature. So most galaxies are so far away from us that we cannot see Cepheid variable stars or any kind of individual stars. But it turns out that within these galaxies, we can still see stars live and die. So here is an image of a star called 2018 GV in a galaxy called NGC 2525. And you can see it being bright and then sort of slowly fading away over time. This is a star that has exploded. And it's exploded and released so much energy that this one star becomes brighter than the entire galaxy that it's in. That is tremendous. A galaxy has something like 100 trillion stars, and one star is now releasing more energy than our sun does in its entire life, and it does this in a single week. We call these stars that blow up supernovae. And these are the sort of things that we're learning in time domain astronomy and want to study more of. We want to see how these stars die. We want to see how they impact their surroundings. But they're very rare. So there's something like 1 to 2 every century in a galaxy like our Milky Way or in NGC 2525. So to find a whole bunch of supernovae, you need to survey a lot of galaxies. So hopefully now I've made the case for A, you need bigger and bigger telescopes, and B, you need to make systematic surveys of the sky. But in all of this time, from the Anasazi all the way to Hubble, be it the person or the space telescope, one thing has remained constant behind it, is that there is a human looking at the data and making decisions. And all of what we've been doing has relied on human inspection and characterization, right? Now, here's an image to sort of drive home this point. This is some of Galileo's observations of Jupiter and its moons. And so in 1612, you can see he's marked Jupiter, the position of its moons, and a background star to sort of identify where things are, much in the same way the Anasazi had a handprint for scale, and the moon and the supernova off on the side to sort of get you a sense of scale for the entire system. And to this day, we do this. So when I was in grad school, I would go look at web pages that had plots of the evolution of the brightness of objects and see the characteristic rise and fall of supernovae as we were doing on that image just previous to this. And I would decide which of these we followed or not by eye. Now, there is a problem with that. One, our surveys are sort of geared to find relatively limited classes of objects. I can only sort of recognize the things that I'm familiar with. And if I see something completely different, maybe I'll reject that and not think it's interesting. And two, it's not really reproducible and it's prone to errors and sort of all sorts of limiting. So if you look at that diagram of Galileo's Jupiter's moon position and that background star, again, it took Charlie Kowal until the 1980s to go back and look at all of Galileo's work and recognize that the thing in the background that Galileo had thought was a star was in fact not a star at all, but was rather the planet Neptune. So he had discovered the planet Neptune and never even known it. And if only Galileo had recognized the planet Neptune for what it was, maybe he'd be famous today. What was particularly funny was he actually did this twice. So this is a separate diagram of Galileo's, again with the planet Neptune, a different part of its orbit. And yet again, he's made the same mistake and thought this is just some background star, not recognizing that it had happened yet again. So we need to do better. We're building better and better telescopes, but we are effectively limited by the fact that humans are trying to characterize the data behind the telescope. So let's now take a little aside and show you the sort of telescopes that we're building. And I'm going to take you to a part of the world that's literally called the edge of the abyss. So if you go down south to the country of Chile, it's an extraordinarily long country, something like 2,000 kilometers north to south, and extremely thin. There's a reason for this geography, and it is 2,600 miles, and just about 100 miles west to east. And there's a reason for this geography, and it's really because the Andes mountain range borders Chile across one side. So it's shoved up against the Pacific on the other side and the Andes on the east. And this particular geography has a consequence. If you look at the north of Chile at a region called the Atacama Desert, because the Andes is running north to south, it blocks the prevailing winds from the east up there, and the prevailing winds in the south are all too far south to affect the Andes. And so effectively, this region is in the rain shadow. It never gets much moisture at all. It's dry, it's barren, it's deserted. And so let's take a trip to a place called Antofagasta, okay? If you look at a satellite image of this region, there's not much there. There's no vegetation almost at all. There's snow and barren rock. If you start to drive past the Chilicos volcano to Antofagasta, you'll see no vegetation at all. It looks Martian. Water is the single most precious resource here. There's a region called the Pan de Azucar where water will flow roughly once a decade after a torrential downpour, and that's it. The only real resource in this region is lithium. There are lithium beds, and if you're watching this talk on a laptop, there's a good chance that the lithium battery inside it came from this part of the world. And in this arid, barren desert, there's a couple of mountain peaks. One is called Cerro Tololo, and this is partly where I did my graduate work. And a little bit south to it is Cerro Pachon, which in the Aymara language of the Atacamenos means the edge of the abyss. So this dry, stable atmosphere in the Atacama does have a major, major plus side for us. So while water is its most precious resource, the second most precious resource that you can have in Chile is a tremendous view of the night sky. Clear, dark skies. You can see the Magellanic Clouds by eye. Here's the large one. You can see so much of our Milky Way, all of these lovely regions in there. It's a tremendous resource because the atmosphere is so still and so free of turbulence. And so in this landscape where we have now one of the most massive engineering projects in astrophysics, and it's called the Vera Rubin Observatory, or the VRO. And what is this thing? VRO is a telescope, and it will begin operations in 2023, doing something called the Legacy Survey of Space and Time, or the LSST. Now, VRO isn't the biggest telescope in the world. It isn't even the biggest telescope right now, and it certainly won't be as we build the Giant Magellan telescope, a 30-meter telescope, or the extremely large telescope. We are really terrible about coming up with creative names for things, so very large telescope is in fact a thing. Now, and we of course want more and more telescope area to collect more light and see fainter and further sources. And we're effectively continuing the same experiment that has run all the way from Galileo through Messier, through Hubble to us. But we also, remember, want to study as much of the sky as possible, to study as many galaxies as possible, to find many, many supernovae, which are rare, which means we need area on the sky. And that means we have to run something called a synoptic survey, get a complete view of the entire sky. And to do that, LSST's construction requires a very, very clever bit of engineering that has 3 mirrors to have a very compact design, but with a very, very exceptionally wide field of view. So while traditional 8-meter class telescopes, something like the Gemini telescope in Hawaii, there's also one in Chile, have a very small field of view, something like 0.2 degrees on the sky. Something like LSST, which has a comparable aperture, it's also an 8.4 meter telescope, has a 3.5 degrees field of view across, which spans 7 full moons. You could just compare those two images on the right-hand side just to get a sense of how much more sky LSST will see than other telescopes today. It's really tremendous. There's nothing else like it. And it is an engineering miracle. Because it needs to survey so much of the sky, there is this thing that is the size of a small building that can rotate something like 7 degrees every second in one direction and 10 degrees in the other. It is quite remarkable to see something this large move this fast. The amount of engineering work that has to go into making this all work is astonishing, and I wish I could tell you a lot more about it, but we simply don't have the time, so I'm just going to push on. But there is one more party trick LSST has. This is one of my academic grandfathers, Bev Oak, holding a 0.24 megapixel CCD. This is minuscule compared to even the small thing, even the cellular telephones that you now have. All of your detectors on your cell phones are, 6, 8, 12 megapixels on. And that has really been the case because of something called Moore's Law. Moore's Law tells us that the number of transistors on an integrated circuit doubles roughly every 5 years. And it was somebody, it was the CEO of Intel, Gordon Moore, who first recognized this back in the 70s. And because the CCD devices in telescopes like LSST that take our data are just transistors on a silicon chip, they obey Moore's Law. So here's Bev roughly at the same time period holding his 0.24 megapixel CCD. Here's Tony Tyson sort of in the late 90s with the big throughput camera, which was a whole 16 megapixels behind him. It's now in the National Air and Space Museum in DC, which you can go see. And Tony is one of the chief scientists for LSST. And here's DECCAM, behind it. Now, the University of Illinois has been a very big part of the Dark Energy Survey, which uses DECAM on the CTIO 4-meter Blanco at Cerro Tololo, just a little bit near Cerro Pochon where LSST is going. And you can see the size of the camera in DECAM. It's this blue thing over here, and that's something like 500 megapixels. LSST is 3.2 gigapixels. So about 4-6 times larger than the biggest detectors that we have right now. It'll pull down 15 to 20 terabytes of data every single night. The entire camera is roughly the size of a Ford F-150 truck and weighs about as much as well. To give you a sense of scale, look at that first lens all the way on the left, the thing that's marked L1. Here's a human being next to L1, just for scale. The position of this lens is tracked to something like 0.01 inches across the entire surface. That's a fourth of the width of an average human hair. It is a tremendous feat of optics. LSST's entire camera is so large it could fit 240 corgis within it. So if you were the queen and you need your numbers and scales of corgis, here you go. No puppies were harmed in the making of the slide, I must say. Okay, so how we know that LSST is going to pull down 3.2 gigapixels each image, so terabytes per night, petabytes per year. How do we look at this stuff? That's more data than you could throw every astronomer at and try to do this visually, and you simply wouldn't have the time to do all of it in a year before you got more data and you'd simply never be able to keep up. So back in the day, people like Hubble, who were working with photographic plates, remember with the VAR, were seeing images like this. LSST is not just going wider on the sky, it's also going deeper. So the technology gets better and better, and so CCDs have improved at the point where something like that big throughput camera that Tony Tyson was standing next to is going to take an image like this with something like the Sloan Digital Sky Survey. Step forward one more generation in detector technology and you start to see fainter sources in the background of the same region of the sky. LSST will do this even better. And so you'll find even more faint sources with even higher signal noise than anything that has been seen before. So it's a really tremendous amount of data that we're seeing, not just because of the area in the sky, but because every single image is looking further into the universe. LSST's catalog is going to have 37 billion sources with a B. There is no number of graduate students that can go through and look at all of these things and decide what objects in there are stars, or quasars, or galaxies, or nebulae. And that is a challenge. If humans can't do this by eye anymore, we'd better come up with algorithms to do this automatically without us having any interference in the matter. And so there are ways to do this. One thing LSST has is a whole bunch of colored glass filters. So it takes color images in different bands and can decide if a galaxy looks more blue or more red, and so on and so forth. And so this is helpful because LSST has 6 of these filters. And so every object on its image has 6 different measurements that tell us something about how blue or how red a particular object is. Now, in an ideal world, we would be able to measure the velocities of things using something like a prism to spread out the light into a rainbow and measure where different lines from chemical elements in these galaxies were. And as you move further and further out in the universe, of course, things are moving faster and faster, as Hubble found. And what we see is that those lines get shifted to higher and higher velocities, higher and higher frequencies, higher and higher frequencies, higher and higher wavelengths rather, and get shifted to the red, hence the term redshift. And so galaxies are constantly being shifted further and further into the red, and we, of course, can't collect this sort of information with LSST directly, but because we have these colored filters, you can imagine these colored filters on top of all of the galaxies that LSST is seeing in each image, as giving you instead a very, very coarse view of the brightness of different sources and how it changes as they get further and further away. Sources at higher redshift should show up more strongly in the red filters than it does in the blue filters. And so I've been working with an undergraduate here, Andrew Engel, who graduated just this May and is now a scientist at a national lab in the Pacific Northwest. And Andrew and I have used a technique called a convolutional neural network. Now, these networks take images and apply operations to them. And Andrew is taking the sort of simulated version of the 6 LSST color filter images and using that broadband information to get an estimate of what the redshift is compared to what you would find if you actually could measure the spectra of the object directly. And he's doing an incredible job of being able to predict what the actual redshift is using this much coarser information and using just the images directly from the telescope rather than using any detailed spectra. And so these convolutional neural networks have become all the rage. They're things that are working behind driverless cars to recognize, for example, if a pedestrian runs out in front of them and the car should apply its brakes. But here in astrophysics, we're doing a much simpler sort of analysis with them. We're trying to use these sort of networks to predict patterns, specifically here, how the pattern of lights from galaxies changes the function of redshift. But we can also learn things about galaxy morphology, whether a galaxy is, say, spiral or elliptical or has a big bar at the center of it or not, if it's maybe a merger of multiple galaxies. This is the sort of work that Andrew is applying AI to do. And so where even a decade ago, a human being would have been trying to look at gigabytes of data from other telescopes to do this by hand, Andrew has now replaced that entire work with one neural network algorithm, one piece of AI. Now, LSST is also going to do a whole lot of other things that are going to demand AI. It's going to make the biggest map of our really rough and violent neighborhood where we have potentially hazardous asteroids, remnants of the formation of the solar system, all zooming around. And there's plenty of good reasons to do this, right? So here's some dash cam footage from a little place called Chelyabinsk in Russia, where a few years ago, an asteroid that we didn't really know about split up as it entered the Earth's atmosphere. And the meteor that we had, because it came in from the sun, nobody has really been able to track it. And it did a tremendous amount of damage, blowing apart doors, such as that warehouse there, on impact as it burst in the Earth's atmosphere, and sending people scrambling every which way. So enough of that hilarity. So LSST is going to do all sorts of other things, right? Remember that we talked about variable stars and how we could use variable stars to get distances. That still remains an interesting question to this day. So we can sometimes see galaxies that are interacting with each other, galaxies that are being cannibalized by other galaxies. And this is our own fate. Andromeda, that galaxy that Hubble found his Cepheid in with a VAR, that's going to collide with our Milky Way in something like 5 or 6 billion years. And you'll have two galaxies get disrupted and form something else. And so there will be streams of stars ripped from one galaxy into the other. And those streams, some of them will contain Cepheids. And so if you could find Cepheids within these stellar streams, you can get the distances of the streams. You can get its position in 3-dimensional space. And that's a really useful thing. In fact, that's such a useful sort of thing too, is to be able to measure rotation curves of these galaxies and understand how these streams work. That the person who first did this, Vera Rubin, discovered that galaxies were not just all made up of the sort of luminous light that we see. What she found looking at a whole bunch of galaxies was, in fact, that if you looked at the rotation speeds of stars as you go out further and further in the disk of galaxies, it doesn't fall off as you might imagine from just the brightness of the galaxies, but rather sort of flattens out and stays constant, sort of contrary to predictions. And these galaxies were behaving like they had much more matter in them than we could count up from just the stars that we were able to see. Matter that we can't see seems to have an effect. We should give this a name. She gave it a name called dark matter. LSST was originally called the Dark Matter Telescope, and it is a wonderful thing that the entire project has been renamed after her, in her honor. it's, I think, a tragic shame that Veera passed away without winning the Nobel Prize. And this in some ways is a small thing that I think our community is doing to make up for that injustice. And that, of course, if you're studying streams of our galaxies, you can study that around our own Milky Way, and you can learn about how the Milky Way's own accretion history has gone, how galaxies have fallen into ours across the billions of years of our universe. And we know that this has happened in the past. We can see streams already from the Milky Way, from a dwarf galaxy, something called the Sagittarius dwarf galaxy. Already, we've seen how these streams work. We can actually test different models for what dark matter is by looking at the structure and shape of these streams, in fact. And so this is cutting edge science that LSST will be the first project to actually do. Now, of course, I'm particularly interested in supernovae, and I told you that LSST is necessary because we need to find lots more of these supernovae, and they're relatively rare. So to give you a sense for that, my graduate student here at the University of Illinois, Alex Galliano, made this video a little while ago. And so time is counting forward as this video increases, and every now and then you'll see a little flash of light, a little dot that shows up. And that's a supernovae going off. And you can see the total number that had gone off up in the top right corner. And you can see as detectors get more and more sensitive, we find more and more of these supernovae. And by the time we're at 2020, we found something on the order of 20,000 of these supernovae. That's cute. LSST will do that in a few months. Literally every supernovae that we have seen thus far, LSST will completely destroy that number in just a few years. And it's particularly important because some of these supernovae are particularly interesting because much like the Cepheid variable stars that Henrietta Leavitt Swan was studying, the supernovae, these particular supernovae, something called type 1a supernovae, also have a relationship no longer between a period and a distance, but rather how fast they decline and how bright they are. And so if you can find these type 1a supernovae, you can calibrate them all to have roughly the same brightness. And if you've done that, you can get the distance to galaxies. And because, like I showed you from that Hubble image of supernova 2018 GV fading away, since these things are so much brighter than individual stars, remember they release the entire energy of something like the sun, except in a few weeks, you can find them at much greater distances. And because you can find them at much greater distances, you can now measure distances across the universe at higher and higher redshift. And so what you're really learning about is how the universe evolves over time. And that's sort of the core of what my own science is. And so a clever game then becomes, how do you identify something like type 1a supernovae from other supernovae or other things that go bump in the night? And to do that, we've been using a variation of predictive text on your cell phone. Now, when you sort of start putting in a word on your cell phone, Google doesn't know what language you're using. It doesn't know anything about grammar. It simply has a lookup table of basically frequency. If you enter these words, then there's this much of a chance that the next word that's going to be entered is something like this particular saying. And so this algorithm, again, doesn't know anything about language. If this video is a little bit clearer, you would see that it's mixing French and German and English all in the same sentence. And so we figured we could use it instead of trying to predict the next word in the sequence to predict the next amount of brightness of a particular supernovae given everything else that it's seen in the past. And so this is what Daniel worked on as a graduate student at Cambridge. He's hopefully going to be graduating in the next few months. And what we did was build a library of a whole bunch of different kinds of explosions that have been seen by other telescopes. And we feed into this algorithm no longer words in a sequence, but rather how the brightness of this exploding star evolves across time. And what we ask Rapid to give us is a confidence that the next brightness is going to be something consistent with a particular class. Same concept as this algorithm, same sort of AI technology, except now being used to sort of identify whether an object is a type 1a supernovae or some other class of exploding star. And you can see that as this algorithm gets more and more observations, its confidence in this particular object being a particular class increases steadily, while its confidence that it is not all of the other classes declines in proportion. So we become very sure after just a few observations that what we're looking at could be a type 1a supernovae or something else that's potentially of interest. And that's really helpful because, of course, if you can identify type 1a supernovae photometrically, again, remember LSST has so much data that we can't get spectra of everything, then you can make the same sort of diagram that Hubble did back in his day. You can remake figure 1, except now with more objects. And we've, of course, done this because we have something like 20,000 supernovae already. So this is a paper with Dan Skolnick and others that others led a few years ago. That's sort of the state of the art of where this is right now from all of the big surveys that we have done. These are effectively the legacy of experiments that Messier and others started. And where Hubble's own diagram fits in there is that just that very narrowest first pixel. So you can see how much further we're looking into the universe than we could back in his day. And yet still we see that as we go out further in distance, things keep moving faster in velocity. The universe continues expanding. But the key discovery that happened in 1998 was that yet again, things were not quite all what they seemed. And it wasn't just that galaxies were expanding away from us. It was that the universe was expanding at an accelerating rate. Something is pushing galaxies apart, ripping the universe apart, as it were, further and further. Now, of course, if you need to cause an acceleration, then you need to apply a force. And if you need to apply a force, you've done work. And if you've done work, you've expended energy. And here is something that we're seeing an effect of that's moving galaxies apart, accelerating them apart from each other at an expanding rate, that's expending energy, but we don't know what it is. And so much like dark matter, we have to come up with a name for it, so we call it dark energy. And that results in a pie chart for our universe of what's actually in there. There's this visible stuff that we can see, stars, planets, you and me, and we make up roughly like 5% of the universe. There's this dark matter stuff that's causing galaxies, like Vera Rubin saw, to behave like there's a whole bunch of matter concentrated at the center and have very flat rotation curves. And we call that dark matter. And then this dark energy stuff, which we also don't know about, but is causing galaxies to move apart faster and faster from each other. And that makes up like 68% of the universe. So roughly the stuff that we know and understand completely is only 5% of what's out there. So there's a huge motivation from the physics side to keep building these bigger and bigger telescopes and studying our universe in greater and greater detail to actually understand fundamental physics through astrophysics. And so even though we don't completely understand what dark matter and dark energy is, we can still use the fact that we understand and can measure how much of an impact they're having to draw an image of the universe. We think it all started off at a hot big bang. The universe gets very much bigger very, very quickly in a few seconds through a process called inflation. That inflation leaves areas that are slightly higher in density and slightly lower in density, slight overconcentrations of dark matter and slight underconcentrations. Those overconcentrations and underconcentrations start attracting other bits of matter through gravity and growing. And so as you go further and further forward in time, there are some regions of the universe that get much more dense, some regions of the universe that get much lighter, and you have this web structure, what we call the cosmic web of interconnected nodes of lots of high mass with streams connecting things to other regions of the sky. And the fun thing is we can do simulations of how this would look. And so if you could actually see dark matter with your eyes, you would see these large overconcentrations of matter on the left. But since dark matter is invisible to us, what we see instead are just the galaxies. And so there are some regions of the universe where we see large clusters of galaxies with many, many things in a very small regions. And then there are these extended tendrils, filaments stretching between these nodes, if you like. And that's really cool because if you have high densities of galaxies in one place, they actually bend light towards us. And that's really useful because you can use them as sort of a magnifying glass to find supernovae at even higher distances. So this is a distant galaxy near a cluster where a supernova went off. We call the supernova Refsdal. And because this galaxy is lensed, there's multiple images of the same thing. And so you have an Einstein cross, a lensed version with 4 images of the same supernova because light is bent by this big cluster of galaxies. What's particularly fun is this cluster is so large that it lends light so much that there was actually a 5th image that we found a little bit later on. There are very, very few of these systems, still a handful of them. And this will change dramatically with a survey like LSST, where we'll start to find hundreds of them. And identifying these sorts of systems is, again, a job for neural networks. And so we're actively using the same sort of convolutional neural networks now to look for big arcs on the sky, to identify lens regions of the sky, and potentially look for anything that changes, becomes variable, using the sort of code that Daniel built, right, to find these things as they blow up in a completely automated manner. With another student, Alex Galliano, we've been inverting the problem. So rather than trying to learn about galaxies from the supernova that go off in them, we're trying to learn now about the supernovae using the galaxies that they blew up in. And what Alex is doing is taking different kinds of supernovae and looking at the kinds of galaxies that they're in. And he's seeing that different supernovae sort of seem to live in very different looking galaxies in this image. And so now, if you know something about the galaxy, even before it's had a supernova go off, if you simply know something about a galaxy, you can now make a prediction for what kind of supernova is going to happen in that environment. And that's really cool because that lets us prepare for things in advance. And it's really useful to also spot stuff that we haven't seen before. So the sort of surveys that we've been running thus far are not like LSST. They've been having relatively smaller, they're using much smaller telescopes and using sort of roughly 4 or 5 day cadence images. They come back every 4 or 5 nights and take another image. And that sort of means that the kind of objects that we find thus far are all in one region of space where they all have timescales that are longer than 4 or 5 days. But there's this big gap of stuff in here where we haven't found transients. We don't know what lives here. And that's really just because the current surveys that we have aren't as good as LSST and haven't probed this sort of range of space. We think there's stuff in there, we just don't know what it is. And so we'd like to identify it. And so we've been using AI yet again for this sort of task. We can build up models of the things that we've already seen on the sky, things like Ara Lyrae and Cepheids, and we can see how they spread out in space. And you can see as I'm moving my mouse, you're seeing different light curves of these variable stars, this Ara Lyrae. You can click on a particular point and get all of the information from big surveys that exist currently about this particular object. You can select entire classes of objects and see how they differ from other classes. For example, Ara Lyrae look very, very different from, say, eclipsing binaries, which are 2 stars going around each other. And so that's really, really helpful because we can start to upload new objects to this sort of same space of looking at light curves and looking at properties of light curves and see if the same objects, see if a new object fits within this map of what we have for the night sky of things that are already there, or if they look very, very significantly different. And so we can spot things that are outliers, things that we haven't seen before, pretty easily. And that's a really important thing because very recently, other than LSST, there's been one other experiment that's been changing our universe. And that's a thing that's called the Laser Interferometry Gravitational Observatory, or LIGO. LIGO is not looking at photons, it's not looking at light, but it's looking at ripples in space-time, and it's finding some of the more rare and exotic events in the universe. So if you remember all the way back to supernova 1054 and Messier 1, I showed you at the center of Messier 1 from this Hubble image, there's a spinning neutron star, a pulsar. Every now and then, there's a couple of those neutron stars that are near each other, a binary neutron star system. And sometimes they merge. And when they do, they create another big explosion called a kilonova. Now, these kilonovae are much less bright than supernovae, they rise much faster and decline much faster, so they're gone within something like a week rather than a month for something like a traditional supernova. So you'd better be very, very fast about finding them. And you'd better, again, be able to identify the sort of galaxies that they're in automatically. You'd better be able to get the redshift of them automatically. So all these bits of AI that we've built individually all come together for this one experiment to try to identify these rare stars that produce most of the heavy elements. Things like gold come from Kilinovae. And to show you, to give you a sense of exactly how rare they are, we have found one, period. That's it. With LSST, we hope to find several a year, but these things are so rare that we will never have as many of them as we do our regular supernovae. And so this is really driving home the reason to build these more powerful telescopes that go wider, that go deeper, and give us faster surveys that are key to understanding our universe. And simply a result of doing that and the sheer volume of data that results from that demands that you use AI to sort of understand things so that we can have a consistent analysis, so we can find things fast, so we can identify things without having millions of grad students, because that's simply never going to be a situation that astrophysics will ever find ourselves in. And so here at UIUC, we're really at the forefront of doing this. Between NCSA, the National Center for Supercomputing Applications, the Astronomy Department, the Physics Department, plus Centers for AI, well, that was interesting. So between all of the centers in Illinois that are tackling this particular problem, we are really at the cutting edge of this field, and we're leading the effort to make really tremendous progress with LSST. So you'll have more results in the future once the survey turns on in 2033. But I hope that when you hear them here at the Kaler Science Lecture, you hear them not from me, but rather from the grad students, the folks that I highlighted who are doing the work, who are in the trenches right now. And with that, I'll take any of your questions.
All right, thank you, Gautham. Folks, if you do have any questions, feel free to raise your hand among the participants, and we will unmute your microphone, allow you to unmute your microphones, and then you can ask the questions that way. If you want to put them in the chat, you're welcome to do it that way as well, okay? Okay, I see a question here from Jeff Bryant, so I'm going to mute his microphone. Did I do it correctly? No?
Yep, can you hear me?
Yes, I can hear you.
Oh, good, excellent. The question that kind of popped into my head, and I'm not sure if you can answer this or not, but since you are studying supernovae, we know that type 1a supernova typically come from a white dwarf, correct? That collapses into a neutron star. White dwarfs come from solar mass stars. Solar mass stars typically have a lifetime of about 10 billion years total, right?
Yep.
So as you look further back in time, would you see, I mean, it sounds inconsistent. You'd think that the further back you go, you wouldn't see as many type 1a supernovae because they wouldn't have had time to evolve to get a white dwarf.
This is absolutely true. So as you go further and further back in time, eventually you will reach a time beyond which the universe is simply not old enough to have formed white dwarfs. Now, there are a few ways that you can get a white dwarf from stars that are more massive than our sun, and it takes a little bit less time. But by the time you're sort of back around a redshift of 2, which is roughly something like 3 or 4 billion years after the Big Bang, there's not a whole lot of these type 1a supernovae around, or not a whole lot of type 1a supernovae around, because white dwarfs are just not being formed at these early times. But there is one other effect. As you go further and further back in time, you're also looking at a larger and larger volume. You're looking at more and more galaxies. And because you're looking at more and more galaxies, you can still find statistically a whole bunch of supernovae out there. Because the volume that you have in our nearby universe, the local group of galaxies, there's just something like 50 odd in there. But by the time you're at redshift 2, you're looking at so much more volume. There's millions and millions of galaxies. So there's still millions and millions of supernovae. And it's also the white dwarfs and the neutron stars are actually not that connected. So the thermonuclear supernova, the type 1As, when the two white dwarfs or white dwarf and another star, when they go boom, there's really nothing left of the white dwarf. There's no neutron star or hopefully any remnant. In the situation where we think a white dwarf blew up around a star like our sun, that star might remain, but it's still going to have had one heck of a kick from the fact that there's a big supernova that just went off next to it. So its entire atmosphere is going to look quite a bit different after that explosion, and it's going to actually start moving very, very fast in one direction.
All right. Well, thank you. That was a great question. Any other questions, folks? Feel free to raise your hand, and we will. Okay. I'm going to lower Jeff's hand. I assume he's asked it.
Oh, it's really cool looking at the participants list and actually seeing some of my colleagues and old friends from Tucson and other people here, and even from IWU.
All right.
So Tanya asks me what made me interested in studying this field. My granddad was a librarian. He worked for the British Council Library in India. And one day he brought home this book by Sir Patrick Moore, who's an English astronomer. And it was, I think it must be the early 1990s, but it was a book that was sort of in preparation for a big catalog that Patrick Moore had. And it had this giant picture of the Andromeda galaxy, M31, where Hubble found his VAR on the cover in black and white. And I must have stared at that picture, I think, for hours. I don't have a copy of that book anymore. It's still in India. My mom has probably donated it now, but I can still tell you what every single page has on every single one of those things. It was just a very visual science, and that was a beautiful, eye-opening picture that was quite literally out of this world.
Very cool. All right, we've got another hand raised here. I'm going to unmute a student with the last name of Pavlovsky.
Hi, can you hear me?
Yes, we can.
Okay, so I'm a bit of an amateur in this field, taking my first course in astronomy. So for someone like me who isn't as well versed, could you explain dark energy and dark matter a little bit more?
Well, so I should really tell you to swing by my ASCO 210 class. We should be talking about this in the last week of the semester. But there's not actually a really great answer to your question, right? If we knew what these things were, we wouldn't study them. Our best model for dark energy is that space, by virtue of it just being space, comes associated with a little tiny bit of energy density. And so as the universe expands, and you create more space, that amount of energy gets larger and larger and larger. And consequently, you have things being pushed apart. This particular model for the dark energy is something called a cosmological concept. And it's a natural part of Einstein's equations of general relativity. And it's unlike anything else that we've seen. So we're not 100% certain it's the right model yet. And this is partly the experiment that NSSD is trying to do and study. And so what it's going to do is not just look for supernova in, the reason it needs so many supernovae is it wants to find a whole bunch across a range of redshift such that you can make a measurement of dark energy in different bins in redshift. So between like 0 and 0.5, 0.5 and 1, 1 and 2, and you can see if the effect of dark energy is consistent across all of those bins. And if it is, then maybe it's a cosmological constant. But if it starts to change as you go back in time, then perhaps it's something else. And measuring how it changes as a function of redshift will tell us what it is. For things like dark matter, there's a ton of models. There's every theorist, what their salt has got their own little pet dark matter model. And so there's a whole bunch of experiments, including things like LSST, but also including vats of heavy water doped with xenon in the middle of mines in Sudan and Minnesota that are trying to detect these particles as they stream through the Earth, the little flashes of light that they might cause. And so those are sort of all direct matter detections of dark matter. There are people who are flying high altitude balloons to look at these things. There's just a ton of different experiments out there. Our best guess for what it is right now is that it's a particle kind of like a proton or a neutron or something of that nature, but it's much more massive. And it doesn't interact in the same way as the regular particles we know. It doesn't interact with the electrical force at all. It sort of interacts with gravity and something called the weak nuclear force, which is responsible for radiation. And so we call these particles WIMPs, or weakly interacting massive particles. There are other models for dark matter out there. There's too many of them to actually summarize here, but we will learn about this in the next decade. So I shouldn't be the one to even try to summarize this. Hopefully you'll have an answer soon.
All right. We've got another question here from Andrew. It says, the more matter a black hole consumes, it gets bigger and hotter. Will this affect the production of stars?
No. So black holes are minuscule things, and space, it turns out, is incredibly, incredibly big. And for the most part, the characteristic distance between stars, so our nearest star, for example, Proxima Centauri, is 4 light years away, and a bit, in fact. So while black holes can get bigger and bigger, and you can get supermassive black holes in the centers of galaxies, galaxies are so large that, and things are so far away from the center, that there's always spiral arms for these big spiral galaxies, or extreme regions that are in the halos of galaxies, where there are clouds of cold hydrogen that will collapse and will still have star formation for billions and billions of years to come. This is not something to worry about at all. Eventually, yes, galaxies will get so far away, and hydrogen will eventually be so exhausted that you won't have stars turning on very much anymore. But by that point, the universe is also expanded, so you're not really seeing a whole bunch of galaxies, and so things slowly get dark and turn off. And maybe that's a little depressing, but I actually find it almost poetically beautiful. You know, here we are at this moment of time, a random species that has evolved because supernovae blew up somewhere, seeded the universe with the elements that came into us and made us. And we are trying to understand where we are in a universe that's expanding and is on its own merry way that has absolutely no care for us. And I find that quite beautiful.
All right. All right, looks like we've got a couple more questions here. We've got one from Molly asking for a little bit more information about Kepler the Wonder Dog.
So Molly is a good friend of mine from college, and she's well aware of my my puppy, who is silently sitting with my wife, and I think begging for tacos right now. So he will not be making an appearance. But Molly is, of course, welcome over any time to hang out with Kepler, as are all of you. If you happen to be in my Astro 210 class, every now and then Kepler makes an appearance. So should you choose to show up one of those lectures, just let me know and I'll break him over for you.
Great. And then we got a question from Lee here. What are the tools for measurement on how you know how deep in space objects are and how you measure energy in space? So a 2-part question.
Right. So by deep, I'm going to interpret it as distance, how far away things are. And so that's partly these things like type 1a supernovae that you can calculate the brightness of. And because you can calculate the brightness of, you can, and you know that objects that are half as bright, there's an inverse square law relationship between brightness and distance. So an object that's twice as far away will be 1/4 as bright as something else. Lets you measure distances just via that inverse square law. Closer in, where you don't have, when you're only looking at galaxies in our local group, then you can use the Cepheids that Henrietta Leavitt Swan used. Even closer in, you can just use trigonometry, a technique called parallax. So if you look at the same star that's nearby and see it move against the background of even more distant stars, you can measure the angle by which it's moved, and then you set up a little triangle, and as long as you remember your trigonometry, then you've set up a little tangent, and you can use that to get a distance to that star by measuring it at opposite ends of the Earth's orbit, for example. And it's just those same 3 techniques that get us all of our distances in the universe. As for brightness, the CCDs or energy, that's really through brightness in the optical. And so our CCDs are essentially counting the number of photons that we get, and that is directly proportional to the brightness of sources. And so if you can measure how strong the signal is on your CCD, then you can calibrate that back to a brightness on the sky to get energy out relative to something that you know.
Great. Folks, did anybody have any other questions for Dr. Narayan? All right. Well, Waylene and I have our mics, so I guess I'll give you a round of applause right there. So much for taking the time to share this with everybody here. It was really great. Now, folks, if you want to stick around for Fall Prairie Skies, Waylene will get set up here. In fact, I can actually just start going and putting her on the spotlight. But yes, thank you once again, Professor Narayan, for your time and sharing with us. We will have another speaker for the Kaler Science Lecture Series in is it 4 weeks or 5 weeks? I can't count today. It's going to be 5 weeks from now. The first Friday in November, we will have a professor, Katie Huff from the University of Illinois, talking to us, I believe, about nuclear reactors. I can't remember the exact details of that talk, but you can find the information on our website, and we'll release a press release in the coming weeks. Okay, so once again, thank you all for joining us this evening. I will press stop on the recording shortly, and we'll start a new one here. In the near future, we may be posting these talks to our YouTube channel, which we recently started. But yeah, once again, thank you all so much for joining us. You're a great audience for sharing all those great questions with us. Okay, so have a wonderful rest of your evening, or feel free to stick around to dismiss anybody out of the dome. It's so nice.
All right, I'm just going to set up here.